This is the last official PowerPoint of the class. Of course, we leave safety for last, but no, safety should always be first on a job site. But, you know, it's good to have it last so it's something you remember from the course. And also, if you're going to do the class tomorrow, on Friday, you'll have some safety things to think about while you're on site. So I've got some things on the internet I want to show you, but maybe we'll just start off and talk about this first. All right. This is I don't know if I've showed you all this picture before. The site that's on the screen it's called, I don't know what it's called. It's called Bunn Solar. It was called Progress 1 when it first got built. It's an O2 energy site that is out in Bunn, North Carolina. The town of Bunn is up here at the top of the picture, and then the prison is down here. That's actually a prison right there. There's a guard tower. So it's a very safe solar site because you've got to go by a gun-wielding guard tower to drive down the road. But this is right after the site got completed, and it looks like there's a lot of muddy dirt around, but it was reseeded with grass, and it grew over really quickly. And now there are sheep and donkeys on that site that are maintaining the grass. It's a 3.5 megawatt AC site, meaning 3.5 megawatts of inverters. Actually, it's 4. I'm sorry. It's actually 4. There are 8 500 kW inverters, and it's hard to see, but there is an inverter pad right here, and there's an inverter pad right back there. And then the point of delivery to the grid is over here at the street. There's a 3-phase power line. There's a pole, which is like right here, and then it runs across the street and then up to the substation. And so all the wires are underground. There's a medium voltage underground connection between this pad with the transformer and that pad with the transformer. And if we have time at the end of class today, I can show you some more pictures of this site and a couple other of the larger solar farm sites. I think the pictures are pretty interesting. So at any rate, this site has been online for 2 years now, just a little over 2 years, and it has been super reliable. I mean, almost no downtime at all. You know, occasionally an inverter will have an issue with the circuit board or a contactor or something like that, but you know, it's never been off. The whole site's never been offline, and the inverters have only been offline, you know, for 1 or 2 days a year, 1 or 2 of the inverters. It's really been amazingly reliable. I hardly have to do anything on the operations and maintenance front for the site, and we've got a great O&M contractor that takes care of it, and you know, he's constantly monitoring the data, and we all get emails and alerts if there's any problems with the site. It's been super reliable. It's very spread out. I mean, it's very elongated. It's kind of an oddly shaped site. But I think it looks good from the aerial photo. So anyway, that is a site in Bunn. And actually, we're building a site just down the street from that. It's being built right now. I'm going to go out there again next week. It's called Cirrus Solar, and it should be online before the end of the year. And it's actually a very similar site. It's slightly larger. That site is 4 megawatts AC. The new site is going to be 5 megawatts AC, and we're using a newer inverter. Instead of a 500 kW inverter, we're using 3 1.67 megawatt inverters that are made by Eaton. I think they're pretty cool. You can go to the Eaton website and check them out. Each inverter sits on a pad and is directly coupled to a medium voltage transformer. So for a 5 megawatt site, we only have 3 inverters, and each one has its own transformer that a loop feed around to the point of delivery. I think it's pretty slick. I'm excited to see it come online. There's not very many of these Eaton inverters that have been installed yet in the country, but maybe only 20. So it's a pretty new technology to have an inverter that large, but I'm excited about it. Okay, so back to safety. Let's see. So I want to talk a little bit about OSHA. So OSHA is Occupational Safety and Health Administration. And also don't forget that there's a chapter in the textbook, chapter 18 in the textbook is on job site safety and goes over some of these issues in more detail, and also covers system commissioning in more detail. Let me see what page that's on. So it is, hold on, give me 1 second. Well, never mind, I can't find it off the top of my head. But at any rate, Chapter 18 is the safety, and in that section there's also a commissioning section as well. So Occupational Safety and Health Administration, there are 2 standards that apply to PV systems in general. There are the construction regulations, which is Part 1926, and then there are also general industry standards, which is Part 1910. And the difference is that when you are building a PV system or installing a PV system, you have to comply with Part 1926 for construction. So if you're out on the site, putting modules on the roof, climbing up and down ladders, you know, the construction part of it. General industry is different. That's going to be things like, those are the rules that apply to the warehouse. You know, if you're in the warehouse and you're moving pallets of modules around, or if you're out on a site and you're doing operations and maintenance. That's not construction. That's going to fall under the general industry standards. And honestly, I think the general industry standards are stricter in some ways than the construction standards. One example is that you need fall protection if there's the potential to fall more than 6 feet in the construction standards, whereas for general industry it's 4 feet. You need to have, you know, handrails or safety if there's the possibility of falling from a height greater than 4 feet in the general industry standards. So these are really big books. There's a lot of information in here. And I don't know how many of you have taken an OSHA 10 or an OSHA 30-hour course before, but I would highly recommend it, at minimum, to take an OSHA 10-hour course before you start to work in the PV industry. And a lot of companies are going to mandate that before you can even go on their job site. And it's also a requirement for the NABCEP, not the entry-level exam, but the NABCEP professional installer exam, professional PV installer exam. You have to have taken an OSHA course prior to taking that exam. And they're offered really frequently. You can even take them online. One of the problems I've had with OSHA courses is that they have a hard time applying to some of the things that we do in PV. One of the things that we do in PV, we'll talk about next, is we have to do a lot of fall protection because we're working on roofs. And a lot of fall protection is designed not so that you can work on the roof, just so that you're going to be safe if you fall off the roof. And that doesn't really work for the PV industry because we need to have what's called positioning as well as fall protection. You know, if you're just on a roof with a fall protection with a harness and a retractable safety line, it's not going to allow you to position yourself on the roof so you can do work. And we fall into this kind of there's a lot of gray areas in there where a lot of the traditional OSHA rules are really not good enough for the things that we're doing, working with electricity on steeply pitched roofs. Of course, there's a lot of rules that do apply, but there's also some things that, you know, are a little hard to deal with. So the NFPA 70E is electrical safety in the workplace. And if you look in OSHA 1926, what it's going to say is that you're required to follow the NFPA 70E rules. That it sort of defaults to saying the rules for electrical safety are not in OSHA Part 1926, but that it's going to refer you to NFPA 70E for electrical safety in the workplace. Give me just 1 second. I just took it out. I'm going to grab it and show it to you. Hold on 1 second. Sorry, I meant to grab it at the break. But so this is NFPA 70E, and you can see that it's not very big. You know, it's less than 100 pages long. It's not a very big book, but it's all about safety when you're working on different voltages and different, you know, arc fault current hazards of electrical equipment. And most of it really refers to the AC side and not so much to the DC side, but it's really critical, and you can take classes just on NFPA 70E. There's also an NFPA 70E handbook, which is a little bit thicker, which is going to help you interpret what the heck NFPA 70E is telling you to do. So the reason I had this out was I was just looking at it this morning because I'm going to go to a system commissioning for a larger system that has string inverters. And I wanted, and we've got these big panel board switchgear that we've got breakers for all of the inverters, and it's 480 volts. And so I wanted to know what PPE I needed to wear, what personal protective equipment I needed to bring to the site if we're going to be opening up this big panel board and working on this three-phase 480 volt system. And so there's a chart in here. I'm not going to be able to find it right away, but there's a chart that says, all right, well, if you're going to be working on this switchgear, you need to have, a face shield, and you need to have a hard hat, and you need to have insulated gloves, and there's an actual list of what safety gear I need to bring to the site if I'm going to be working on this piece of equipment. And of course, these are things that often get ignored, unfortunately, in the PV industry. I think we're really playing catch up a little bit with some of our safety regulations. That's true of a lot of electricians. A lot of electricians are not complying with NFPA 70E, which is horrible because electricity can be really dangerous, and you never know when you're going to make a mistake. Mistakes happen, and electrical mistakes can be horrible, and they can kill you. And if you take an OSHA class, I think what you'll find is that what they do a lot of times is show you these really horrifying videos. People falling off towers, art blasts, and electrical gear equipment where people catch on fire and die. They're horrible. And horrifying as well, but it's all true. And the point is that you can buy the right equipment. It's not very expensive, and you need to wear it when you're working on electrical equipment because you just never know. You never know what the heck is going to happen. There was a couple of electricians that got killed in California last year when their meter exploded in their hand. You just don't know. It may not be a mistake that you make. It may be a mistake with the equipment. It may be a mistake with a piece of equipment. You can have breaker failures. You can have wire insulation failures. Even if you trust yourself, it doesn't mean you should trust the people you're working with or the equipment manufacturers. So that's NFPA 70E. The electrical code is NFPA 70. So these two things go together. There's a whole bunch of NFPA documents, but electrical code is NFPA 70. Safety guides are 70E. So there's that. And you can take classes on the OSHA requirements, and you can take classes on the 70E requirements. So if you go through one of these classes, what they're going to tell you is that OSHA is there to protect employees, not employers. And they're going to say, if you own your own company, if you work for yourself, you don't have to worry about OSHA coming in and giving you a fine. And while that is true, I wouldn't think that that's necessarily an appropriate way to behave. What that means is that if you own your own solar installation company, you can get up on the roof without any safety equipment. You can work in the electrical cabinet without any safety equipment. OSHA doesn't care. It's your company. You can kill yourself if you want. However, if you have employees, the employer needs to make sure that they have the safety equipment available that's needed for the job site. The right PPE has to be available for the employees, and the employees have to have gotten training in how to use it and when to use it and where to use it. And if that doesn't happen, then OSHA, and if they're not using the equipment, then OSHA can waltz into job sites anytime they want and give you an extremely large fine, $70,000, $100,000, and they get bigger every time they fine you. And it happens because, PV is a growing industry, and as a growing industry, we see more deaths in the industry. So it's definitely on OSHA's radar, and they have been fining companies and handing out citations on PV projects. The other thing just to be aware of is that OSHA can fine you, your company, just based on pictures that are in the newspaper. So, if you're getting some media attention for your company, you should be careful about the pictures that you post on your website and the pictures that you post that you let media take, because SEI, Solar Energy International, actually got fined by OSHA, an installation that they were doing in Washington State. There were some pictures of students on the roof that weren't wearing the right safety equipment, and they got an OSHA fine because of this picture that was in the paper. So it definitely happens. And I've got some other friends who have had that happen on their job sites as well. So, the fine shouldn't be the motivating force here. What should be the motivating force is that you really, really, really don't want people to get injured on your job site or killed. That is just, it's a terrible thing to have happen. You know, it's terrible for the families of the people who get injured. It's terrible for the company that's doing the work. It's just terrible for everybody. And so a lot of the OSHA requirements, what they say is, look, you know, accidents happen. What we want to do is identify the hazards and try and mitigate the harm. So every morning when you go onto a job site, you should have a safety tailgate meeting and say, okay, what are the hazards on this job site? Well, there's ditches, there's other contractors on site with heavy, you know, skid steers and lulls, that there's people working on the roof and they could drop something off and it could kill you. Someone got killed just a couple weeks ago. I think it was a tape measure that fell off a roof and hit somebody on the head on the ground. You know, those things can kill you. And so what are the hazards and what are we going to do to mitigate the harm? Well, there's people working on the roof and there's people working on the ground. What that means is that everybody on the ground has to wear hard hats, or we have to have a controlled area at the bottom of the roof where nobody can walk. If nobody wants to wear hard hats, although I would say you should probably just wear hard hats. You need to have netting up on the roof so that things can't roll off the roof. So that's worker safety. Something to think about is anytime you go on a residential job site, there can be kids around. And if you've got workers working on the roof and they drop a wrench or they drop a screwdriver or they drop a tape measure, the thing's just going to roll off the roof. And you really don't want a kid to be walking by, you know, getting on the school bus, walking to the front door, and have a tape measure fall off the roof and hit him in the head. I mean, that stuff happens. So thinking about not just the employees, not just the workers on site, but what can go wrong on a job site. So having safety tape, caution tape, taping off work areas, taping off trenches, making sure that if you're digging a trench through somebody's yard, you know, the kids don't come and fall into the trench. You know, just identify the hazards and try and mitigate the harm is really if you go through an OSHA 10-hour class, I think that's a lot of what you come out with is what OSHA wants you to do is create a safety plan for your job site every day and follow it. Accidents happen, but you need to make sure that the people on the job site are aware of the hazards and they have the right safety equipment and the right setup to be able to mitigate the harm. And you know, if you've got written records, if you've got training records, then OSHA's not going to fine you. You know, if you tell an employee, look, you need to wear this PPE, you need to have this fall protection, and you're their employer, and you've got it written down, you've got records, and you go to lunch and they take it off, you know, you don't get an OSHA fine for that. That's not your fault as the employer. But if you don't give them the right PPE, if you don't give them the right training, you're going to be in a world of trouble if OSHA comes by your site. A world of monetary trouble. If nothing bad happens, you'll just get a hefty fine. But if something bad happens, you know, it's terrible. So anyway, this picture on the screen, I actually took this picture. I went to India to a solar conference, and you know, I just saw this happening. So here's a guy up here with no PPE on. He's on a bamboo ladder, a very tall, rickety bamboo ladder, and he was actually swapping, I think he was swapping out a transformer on this pole without any PPE on. It was a little hard to tell, but it was also rather scary. So, okay, so some particular areas of concern in OSHA. So this is part 1926 OSHA. So subpart X is fall protection. So safety on roofs, safety around skylights, which is just a big hole on a roof basically because they're not going to be weight load rated. Open floors on buildings. Any place where you can fall more than 6 feet, whether it's from one section of a roof, whether it's off an open floor, whether it's off a roof, requires fall protection. And fall protection can encompass varying things. Fall protection can be a personal fall arrest system, it can be a net system, it can be a guardrail system, it can be a scaffolding system. There's a lot of different things that can meet fall protection system requirements. And I wanted to just show you a couple of things really quickly. That's not it, but I'll be able to find it. Well, first let me show you this. I really like this. Is a retractable, self-retracting lifeline. And so if you haven't seen these, they are really, really useful. So a lot of times, if you've got on a harness, so let me show you a picture of a harness. This is interesting too. So this is Peterson. Peterson makes some really, really good harnesses, like really good. And if you go to their website and you search for harnesses, what you'll see is two different things. Well, actually a lot of different things, but the two that we're interested in is not rock climbing harnesses. What we want is work positioning and fall arrest harnesses, or just fall arrest harnesses. And so the difference is, this is what's known as a positioning and fall arrest harness. And why it's positioning is that it's got this D-ring on the front. And so if you're working on a really steep roof, you can attach that to a line on a roof, and it'll hold you in position. And that's actually very uncommon to find that in a fall arrest harness. So the fall arrest is this D-ring on the back right here. And so if you fall off a roof, you want your lifeline to be attached to the back. So you fall forward instead of falling backwards. If you're just attached to the front ring, you could break your back when you fall off the roof. So a fall arrest harness is going to have this D-ring that's on your back that is attached to. A work positioning harness, you want to be held by the front so you can work on whatever's in front of you. And Peterson is one of the only manufacturers I know that makes this dual purpose harness. So you can hang on the roof and do work. You know, steep roof, you're going to have to be held in position, and also have the fall arrest harness that you need in case you can fall off the roof. If you compare that to the fall arrest harness, what you'll see is that there's no front D-ring on just a fall arrest harness. So if you're working on a pretty low slope roof and you don't need to be held up on the roof to work, you can just have a basic fall arrest harness like this. You don't need that front ring. But you do need the back ring in case you fall off the roof. If you look at some of the other harnesses that Peterson makes, what you'll see is a lot of them, this is a work positioning C harness, so that might be like you would use on a big tall tower. They also make harnesses that are for like mountain rescue, mountain climbing, all those types of things. But what we're interested in is fall arrest, and that's, to have fall arrest, you're always going to have that D-ring on the back. So what do you attach that to? So one of the best things to attach that to, because remember it's not holding you in place to work, it's just stopping you if you start to fall. This is a really cool lifeline. So you attach this to an attachment point on the roof that's probably going to be nailed in to a rafter or over the ridgeline, or it may, new construction now is mandated to have permanent lifeline attachment points on the roof. And if somebody's getting their roof replaced before you put the PV system in, that's a really good time to get some tie-off points attached to the roof. You know, you put 3 of them across the stretch of the south roof, and it'll make it much easier to install the system and also to maintain the system if you need to go back up there. And so this self-retracting lifeline is just like a seatbelt mechanism. And if you yank on it, it stops you from falling. But if you don't yank on it, it self-retracts like a seatbelt does. And the alternative is what's called a rope grab. And a rope grab, you have to manually move it. So if you're walking up and down a roof and you just got a rope grab, you have to actually pick it up and slide it up the rope, which can be annoying, and people don't do it. And if they don't do it, your lifeline gets too long, and you might be able to fall off the roof in certain places if you're not moving your rope grab. So the reason I like these, they're not all this expensive. This is a rather expensive one. I like these self-retracting lifelines because you don't have to worry about it. You walk normally up and down the roof, it follows you where you go, and if you trip or you start running on the roof or you fall, it'll grab that D-ring on the back of your harness and stop you where you are. So it doesn't get in the way. It's really nice for working on roofs. So I think that's what makes PV a little complicated, is that oftentimes you need both. You need the front attachment for holding you on a steep roof, that front attachment right there, and then you need the back attachment as the fall arrest if you fall off the roof. So that's a lot of ropes to have on a roof, and that's why people will get annoyed about working on roofs, because the ropes get in the way and they get tangled up, and it can be a little bit difficult to deal with. But it's really important, and I'm going to show you a very sad video before the end of class today, so you'll believe me that this is important. Actually, maybe I'll show it to you right now. So, like I said, when you take OSHA classes, I'm sure some of you have taken OSHA classes, they show you these horrifying videos, like really terrible things that give you nightmares. And they're trying to just say, hey, you know, people die, this is important. And so there's a video that I'm going to show you, and I admit it's very sad, but it's not disturbing, like, you know, no blood and gore in the video. It's just sad. And so I just wanted to show it to you because I think everybody should be aware that people are dying in the PV industry when they're not following OSHA requirements and using fall arrest systems. Most of the people that have died working in the PV industry have fallen off of roofs. I only know a few people that have gotten electrocuted. Maybe before I show you this video, I'll show you this fatal facts worksheet. So OSHA, in coordination with other local OSHA programs, does what they call a fatal facts summary. And if someone gets killed on a job site, they'll, for some of the situations, they'll write up like the why and the how and what of it so it doesn't happen again. So this was a few years ago. An electrical worker died. He was walking across the roof of a warehouse, and he was carrying solar modules with another guy, and he was walking backwards, and they hadn't covered up the skylight. And so there's pictures in here. Let me scroll down. There's a picture of what happened, which is that it was this kind of flexible module. And he was walking, and he just stepped right into the skylight and fell all the way through the building, and he got killed. And why that happened was because they hadn't blocked off the skylight or covered the skylight. So you can get covered skylights for roofs. You know, it is really just a big hole. I mean, this is not going to hold up the weight of somebody if you step on the skylight. There are, you know, people-rated skylights, but I don't know if I would trust them. So it's true of any hole on a job site. You know, I think it's 2 by 2 inches. It's like very small holes that OSHA requires that you cover the hole and have a sign that says hole, or you get a cage that fits over the skylight. And so it's just, you know, this stuff does, it happens. Another fatal fact incident that happened was there was a PV installer who was working on a residential job site, and he was hanging the rails up to the roof, and they hadn't looked around and identified the hazards. And when he was hanging the rails up, he accidentally made contact with the overhead power lines where they were attached to the weatherhead on the building, and he got electrocuted and died just because, you know, it's a big long metal rail, and it accidentally brushed against the not a high voltage power line, just the residential voltage power line that was coming into the house. All right, so, you know, you don't have to watch this video, but I wish you would, because it is, I mean, it's very sad, but it's not gory by any means. It's just like, hey, you guys, you know, accidents happen, and the only way to make sure that people don't get killed is to make sure that you're wearing the right fall protection on a roof. Let me unplug this.
For Hans Peterson, Wednesday, April 7th, 2010 began just like any other day. He said goodbye to his roommate and headed off to work as a junior solar installer. He didn't know it at the time, but he wouldn't come home that day. The California FACE program investigates workplace deaths and develops recommendations to prevent future deaths. We made this video to honor Hans's memory and to help prevent tragedies like this from happening again. When we arrived at the scene to investigate his death, the work crew was upset but willing to describe what had happened. The employer was a solar installation company, and we learned Hans had been working there for 6 months. This was the second day at the work site, where the crew planned to install solar panels on the roofs of several 3-story buildings in an apartment complex. Hans, a coworker, and the crew lead were up on the roof checking the alignment of mounting rails in preparation for the installation of solar panels. A pre-job hazard analysis had identified the high, sloped roof as a fall hazard. The employer had a written safety procedure that described the fall protection plan and held an on-site safety meeting the first day. At the meeting, the project manager told the crew that the safety plan called for them to use a personal fall restraint system on this job. However, at the time of the incident, none of the 3-man crew was wearing personal fall protection equipment, and there were no anchor points, guardrails, or safety nets in place. Hans was up on the roof checking the alignment of the mounting rails, walking backwards to possibly get a better look. His coworkers heard him say something and then noticed he was no longer on the roof. Hans had stepped backwards off the edge of the roof and had fallen 45 feet to his death. How could this have been prevented? Employers should ensure that workers use approved personal fall arrest or personal fall restraint systems when working on roofs at height that have a steep slope or have other fall hazards. Hans fell from a roof that was 45 feet high and had a 37-degree slope. Use of a personal fall protection system, including temporary anchor points, guardrails, safety nets, scaffolding, or catch platforms, could have prevented his death. To ensure safety procedures are followed and fall protection is worn, a trained, competent person should perform safety inspections of the job site to check that appropriate fall protection is available and being used. In addition, workers must be provided training in fall hazards and safe work practices, and the employer must keep records of the training and who was in attendance. The FACE program shares investigation findings and works together with employers and workers so this won't happen again.
Like I said, very sad, but true. I mean, I can't tell you how many times I've been on PV installs on residences where no one is wearing fall arrest systems. And I think that, you know, what happens is that everybody says, oh, it's too time consuming and it'll add a whole day to the job, and you know, we'll never get done, and you know, it's not worth it for this quick job to go up there and put attachment points on the roof and to, you know, do it the right way. But you know, if you don't do it the right way, horrible things can happen. So it is very important. And I think that, you know, as companies grow and as they get bigger, it becomes just ingrained into their culture that, you know, you're not going to be working on that roof unless you're wearing fall arrest system. So it gets better. So personal fall arrest. Okay. Oops. Clicked too far. All right, so the second thing I wanted to talk about was ladder safety. And ladders, to be used properly, they have to be extended 3 feet or 3 rungs above the working surface and also be secured. So this picture is a little wonky, but it's actually not quite enough. That should be 3 rungs above the work surface, but I just put this diagram together. The reason, and also you'll actually find ladders that are really good for PV jobs where they don't have these top 3 rungs. And so if you lean it up against a building, you can actually step through the ladder. So you can hold on to the side rails and step through the ladder, and the rungs aren't in the middle. And it's just to make sure that you've got enough ladder to hold on to as you're stepping off onto the roof. So you need to have 3 feet above the top of the roof at that tie-off point. When you're using ladders, you have to maintain 3 points of contact with the ladder. And what that means is that you can't carry a module on your back or in your hand up a ladder, because if you do that, you're not going to be able to maintain those 3 points of contact. So people make module backpacks, they make module hoists, you can get lifts on sites, you can use a pulley system to pull them up another ladder, but you shouldn't carry modules up ladders. It's not safe, especially with how big modules are these days. You know, I don't think you could carry a 300-watt module up a ladder by yourself. I don't think it's possible. You know, we used to have little 60-watt modules, and you could just tuck them under your arm. You probably could maintain 3 points of contact with a ladder. You know, they only weighed 20 pounds. You know, now modules weigh 65 pounds, and they're 6 feet tall, and it's just, you cannot carry them up a ladder. I have a friend in Utah who made a little module backpack that well, it's actually pretty big, but it's a backpack. It holds 1 module, maybe even 2 modules, and you can carry them up on the roof in the backpack. So something like that works, but you can't just carry modules up a ladder, even 2 people. It's not permissible. So the other thing is that ladders have to lean at the proper angle. It should be a 1:4 ratio from the base to the vertical, from the base, length B to length A. So for every 4 feet of working length, the base of the ladder should be out 1 foot from the top support. There's a 25% ratio there. And also, if you're just standing at the bottom of a ladder, there's a couple of things to look for. One is that the rungs should be flat. You know, if you have the ladder straight up, they're kind of at an angle. So the ladder is designed so if it's at the correct angle, the rungs are flat on the ladder as you're walking up it. And also, if you're standing at the base of the ladder and you reach out your arms, you should just be able to touch the ladder. That's usually the right ratio. If you're standing there and you reach your arms out, it's about right. The other thing is that you should be using fiberglass ladders if you're doing electrical work because they're not conductive. It's okay if they've got metal rails, but the outside should be fiberglass on the ladder, so there's not metal conducting all the way down to the ground. Okay. PPE, I already mentioned. Eye protection, you know, whenever you're on a job site, you should be wearing PPE, like all the time. I don't think anybody should be on a job site when they're not wearing safety glasses. These are more like safety goggles like you would use for a battery system, but ANSI Z87 means if you've got a little, if you look at your safety glasses and they've got a little ANSI Z87 mark on the side of them, that means that they're shatterproof. So regular glasses, sunglasses are not shatterproof, so if you get something like a flying piece of metal, your glasses aren't shatterproof, it could hurt your eyes. So ANSI Z87 are the safety glasses that are shatterproof, and you can buy all kinds of cool ones now. If you look online, I don't have them here, but I got some nice bright pink ones so they don't get lost. You can get sunglasses, you can get goggle types, you can get anything you want. You can get prescription safety glasses if you wear prescription glasses. You can get safety glasses that go over your glasses. Anything you can think of you can buy as safety glasses. Electrically insulated gloves for testing energized circuits. So the reason I wrote it like this is because on most PV job sites, as you're installing the system, you shouldn't be coming into contact with any energized circuits. We're going to talk about installation procedures in the next slide, and then on Friday I'm sure you'll talk a lot more about that. But as you're installing the modules, all the connectors are touch safe. When you're wiring up the inverter and the disconnects, you're not going to have connected the power sources yet. And so you don't have to wear insulated gloves when you're installing PV systems. So you're not going to get, there's no energized circuits. It's really just after you connect the power sources and you're doing voltage and polarity testing. That's when you need to wear insulated gloves, or if you're doing troubleshooting in a system. But that's a pretty small amount of time compared to the amount of time it takes to install a PV system. So insulated gloves, you'll have some at the site tomorrow on Friday, I'm sure. But they're thick rubber gloves. They've got leather protectors that go over the outside. They come in different voltage classifications for 500 or 1,000 or more voltage than that. So just being aware that if you're testing on energized circuits, 120 volts, I know most electricians don't wear insulated gloves, but according to this, you should because it can definitely kill you. In general, your skin is resistant to, maybe 40 volts. The touch-safe voltage limit per international standards is 30 volts. So that's the resistance in your skin to voltage, to that pressure. And so it means if you touch a 12-volt battery, you're not going to get shocked because that voltage pressure isn't enough to get through your skin. So the voltage is what gets through your skin. So once you're talking about 100, 120, 300 volts, you will definitely get shocked. What kills you is the current. DC current, AC current, doesn't matter. People talk about, oh, DC is more dangerous than AC, whatever. What it is, it's totally irrelevant. What it is I think people think that because they've worked with low voltage batteries, and batteries don't have a high enough voltage pressure to get through your skin. But it's the current, so milliamps of current. So if the voltage can get through your skin, and 120 volts definitely can, then what's going to happen is it's going to depend on the amount of current and the path of the current through your body. And so a lot of people tell electricians, just use one hand in that electrical box and don't use two. The reason being that, if you've got two hands in an electrical box and you have a short that happens, what will happen is the current is going to get through your skin and it'll flow back to your other hand right through your heart. And that honestly is more dangerous than just having one hand in a box, and if you get shocked, it'll maybe flow through, the right side of your body down to the ground, potentially. Other things can happen too. I've seen people on PV sites where they had a positive conductor in their hand, and they touched a metal junction box. It was actually a pretty young kid. He was about 18 on his first solar site, and the back of his hand touched the metal junction box, and the front of his hand he had a stripped positive conductor. The box was grounded, and it was a negatively grounded system, so there was a fault from positive to the grounded metal, and the current went right through his hand and blew it like a hole through his hand. It was horrifying. You know, dangerous stuff going on. So current levels, 30 milliamps can hurt you. 70 milliamps can kill you. It can stop your heart. That's, when you're working in a 120 volt electrical panel, there's hundreds of amps of current that are available. When you're working on DC PD systems, there's way more than 70 milliamps. So it's really, even small systems have high enough voltage to get through your skin and definitely enough current to kill you. So don't listen to anybody when they tell you that it's safer to work on DC systems. That is a ludicrous thing to say. So electrically insulated gloves whenever you're working on energized circuits. Proper footwear. So I didn't say boots. We talked about this already earlier today, just because the footwear you're wearing depends on where you're working. If you're working on a big ground-mounted system and there's heavy equipment and people drilling and big pieces of metal, you're going to want to wear probably steel-toed boots, or depending on what your job is, you might want to wear insulated boots, electrically insulated boots. If you're working on a roof, you're probably going to wear sneakers. And so there's not one answer for PV work. It really depends on what you're doing, thinking about what the exposure is to and what the dangers are. And roofs are very different. You don't want to wear boots on a roof. Hard hats come in different classes. A Class A hard hat protects against falling objects and also protects against conductors up to 2200 volts. So that's a very important thing if you're on the job site to figure out, do I need to be wearing a hard hat? If there's any danger of falling objects or hitting your head on rails, I would wear a hard hat. If you're working on a roof, probably not necessary. It might just get in your way every time you lean over, it falls off your head. But down on the ground, probably you are going to need to be wearing a hard hat on almost any PV job site, especially if there's other contractors on site. Comfortable is important. Well, obviously, if your PVE is really uncomfortable, you're more likely to take it off. That's a danger because these electrically insulated gloves are kind of horrible to work in. I mean, it's really hard to hold your tools. They're really sweaty. That's why you want to minimize the time you have to wear them, and you want to keep your power sources locked out and tagged out until you're ready to test equipment, because you don't want to be wearing these insulated gloves. You can't really you can't do work with them on. You can't even hold a screwdriver, really. Get comfortable glasses that fit you, get a hard hat that fits you. PPE is really important. It's critical on these job sites. One of the reasons I showed you that Peterson harness is because I think they're really comfortable. Those are really, if you get somebody, the cheapest harness that doesn't fit them, well, for one thing, it's not going to work right if it isn't adjusted properly, but they're not going to want to wear it. And that's why I like those retractable lifelines. I like the Peterson harnesses because those two things together are really easy to work in. They're pretty comfortable. They're actually kind of nice, those harnesses. If it's not comfortable, people are just going to take it off, and then potentially get killed. Okay, so I'm not going to spend a whole lot of time on installation procedures because I think it'll be much easier on a job site to go through these steps, but I will talk through them. And there's also, as I mentioned, a good article chapter in the textbook on installation procedures with better pictures. But in general, step number 1 is always going to be talk about the job site hazards for OSHA requirements and what you need to do to mitigate those hazards, to mitigate the harm from the hazard. So do I need to wear a hard hat? What PPE is required? Do I need to cover up skylights? Do I need to cover up some trenches? Do I need caution tape around the ladders or the edge of the roof? Do we need to build scaffolding? All the things that have to happen before you can get started working. And then also to identify the power sources. Where's the power coming from on the job site? I mentioned the guy who hit the overhead power lines with a rail. That is definitely a power source that you want to be aware of. If you're on a job site and there are utility lines that are in the way, which does definitely happen when you're working on a roof, depending on where the service entrance is, you can call the utility and they'll come out and put these orange insulative blankets over the power lines for the whole time you're working on the job site. They'll do that for you. So when in doubt, call the utility and get them to put these insulative blankets over the power lines. They're just big orange rubber blankets they put over the power lines. That's one power source, of course. Other power sources are, there could be a generator on site, there could be batteries, there could be multiple AC power sources, there could be a PV array, microhydro, wind turbine, who knows. There's a lot of different power sources. And so once you identify the power sources, you need to isolate them from your job site, meaning turn off the power if you're going to be working on circuits. Open the disconnects, open the circuit, and then lockout, tagout. So most residential electricians do not use lockout, tagout. I have very, very rarely seen residential electricians who even have lockout, tagout equipment. It's more of a commercial industrial thing that electricians have, but you should have it on residential PV sites, and it's very cheap. So this is a tag down here in the picture that says, do not operate this switch. A tag doesn't physically keep you from turning the switch on. It's just a notice, and I don't think it's good enough. I think you should have locks. So here's a lock, and if I put a lock on this AC disconnect and I put the key in my pocket, I know that there's no way that some other contractor on the site or the homeowner, they can't come up and throw the switch and energize the circuit that I'm working on and kill me. And it sounds ridiculous, but it totally happens. I've been on job site, where there's a plumber and his extension cord gets pulled out of the wall, and instead of figuring out that the extension cord gets pulled out of the wall, he goes to the breaker panel and starts throwing all the breakers on that we've turned off because we're working on those circuits. And I've had homeowners do that. They're like, I want to watch television, and the TV's not turning on, and what do? They walk up to the breaker panel and they start flipping all the breakers in the panel, every single one, because they think the breaker's tripped when we've turned it off because we are, moving some circuits around and putting in a sub panel. So the only way to make sure that doesn't happen is to use lockout, tagout. Even on residential sites, I think it's really important. And you can get these, they're very cheap. You can get them in all different shapes and sizes. You can get a breaker lockout. It's just a little plastic tab that you clamp around the breaker. Y'all are going to use those on Friday. You can get power cord lockouts too. You can actually lock out the end of a power cord. It's like a big bubble that you put on the end of the power cord. And really almost any kind of a lock works for this kind of switch handle disconnect. So I think it's critical to do that on residential systems. Like you can't keep an eye on everybody all the time. So remove any fuses. So there are fuses sometimes in the combiner boxes. There's fuses in the inverter. You want to take those out before you start wiring up the system because they can cause faults. If you wire something improperly and you've got the fuse in place, then you can create like a circulating loop current through a fuse, and if you try and pull the fuse out, it'll arc. So taking out the fuses is going to help you check the system before you turn it on. So at this point, you're ready to install and wire all the components. You're not connecting any power sources. You don't have to wear insulated gloves. You can wire from the DC disconnect to the inverter. You can wire from the inverter to the AC panel board. You can wire up all the modules. You can bring home runs down. Nothing is connected, but it's all wired up. And at this point, I want to talk a little bit about torque check. So this is a torque wrench right here. And probably a lot of you who've worked in construction have never torqued anything because people don't do it a lot. But every single piece of equipment that we install on a PV system is going to have torque specifications. And what that is it's the torque pressure in inch-pounds or foot-pounds that you are applying to a bolt or a screw or a terminal. So inside the inverter, there's torque specs for all those little screws on the circuit board. Breakers have torque specs. Disconnects have torque specs for the terminals. The racking will have torque specs. Weaves have torque specs, the weaves that you ground the modules with. Lay-in lugs, all of that stuff has torque specs. What that means is it means that if you use a torquing screwdriver or a torquing wrench, which you should, you're not going to over-tighten a connection and you're not going to under-tighten a connection. And both of those are dangerous. If you under-tighten a screw, then it's going to have a lot of resistance and eventually it will catch on fire, likely to catch on fire. It'll get very, very hot. It may even start to pull out. You'll get an arcing fault, and DC arcing faults are hot and they can be very long and they can definitely catch them on fire. That's what happens if you under-torque connections. If you over-torque connections, there's bad things that can happen too. One of them is that if you are letting your new installer over-torque the inverter terminals, they are likely going to break the inverter circuit board. They're really pretty fragile, and they have very, very low torque settings, like 6 inch-pounds, which is a much lighter torque than you would expect. And if you over-torque it, you're going to strip the screw out so it's unusable. And I've actually seen people pop those little those little circuit boards like totally off the inverter. And so by using torquing screwdrivers and torquing wrenches, you're going to avoid damaging the equipment, and you're going to avoid potential fires. So both of those things are important with electrical equipment. And with the rack, you just want to make sure that it's not going to blow away. And if you over-torque rack clips, you can actually damage the module. So all of these things are important. For a rack, you're probably going to be using a torque wrench, like this one right here. And the rack manufacturer is going to say, tighten the mid-clamps to 10 foot-pounds or whatever it is. And then all of your electrical equipment, usually on the door of the electrical equipment, there will be torque specs in inch-pounds for all of the terminal screws in the electrical equipment. I just feel like it's important for making a long-lasting system, but if you're the person, if it's your company and you're sending out some guys to do some work, giving them a torque wrench and teaching them how to use it is going to save you some headaches and equipment that's installed right and not damaged. So critical. Okay. Also visually inspecting the components, making sure that everything looks like it's color-coded correctly, that the wires are all right, that you don't have insulation under a screw. If you're putting a wire into a charge controller or an inverter, checking the color coding on the wires. You're doing all of this before you connect any power sources. So I think step 7, it's a little confusing. So we're saying connect the power sources, but don't close the disconnects. So what this means, for example, is that we'd have our home runs on our PV array. They've got the quick connects, and we go to the pass-through box on the roof, and it hasn't been connected yet. It's all been wired up, but the quick connects are not connected yet. So if we connect the last home run quick connects, mate them together, we're going to have energized the system down to the DC disconnect, which could be sitting next to the inverter. It could be integrated into the inverter. At that point, the disconnect is still in the open position. It's not on, but we can open it up. We can put on our insulated gloves, and we can test the voltage and polarity in the box before we turn on the switch and energize the inverter. And why that's important is because if you make a mistake in your wiring, this is the place where you're going to catch it before you damage your inverter. And one of the mistakes that people make a lot because they have mispolarized their wires is they will connect a negative of one system to a negative of one string to a positive of the other string instead of a negative to a negative. And it's very easy to do that in the combiner box. You've got all these black wires coming in from the roof. You haven't color-coded them right. And if you flip-flop 2 wires, instead of making a parallel connection, negative to negative, what you make is a series connection, negative to positive of 2 strings. What happens when you do that? Well, interestingly, instead of having a 500-volt PV array, you've got a 1,000-volt PV array. Yeah, over voltage, and that happens a lot. And my meter, this is my meter doesn't read 1,000 volts. It only goes up to 600 volts DC. So if I'm in the box, disconnect box, and I'm measuring the voltage, and my meter's going to say OL, and I've seen this happen before, overload. I'm like, that's not a good sign. Do not turn on the switch. Do not, because if you do, the inverter is going to see 1,000 volts, and it's going to damage the inverter, and you're going to void the warranty on the inverter, and maybe blow out some capacitors in the inverter. So checking voltage and polarity in the disconnect before you turn it on is really critical because those types of wiring mistakes happen very frequently in PV systems. Series connections where you meant to make a parallel connection, or a parallel connection where you meant to make a series connection, and what will happen is you can have twice the voltage you expect. It's easy to catch and it's easy to fix. You just have to do your testing before you turn on your equipment. You haven't damaged anything in the system if you do this test before you turn on the inverter. You haven't even damaged the switch because you haven't closed it yet. If you close that switch and then you try and open it back up at 1,000 volts, it could likely arc across the terminals like I showed you in that video. So connecting power sources doesn't mean turning things on. That's pretty critical. Before we turn anything on, we're going to test voltage and polarity and make sure that we see what we expect. So if you expect that the array should be at about 500 volts open circuit, and you don't see that on your meter, you need to take a step back and think about what you did wrong and start troubleshooting the system and find out where you made a mistake. If you read 200 volts, something's wrong. If you read 1,000 volts or overload on your meter, something's wrong too. So it's really, your meter is your eyes and your ears into the system. You can only tell so much by this visual inspection. You really have to rely on your meter. And when we talked about meters, I mentioned that what you really should need to do is test your meter on a known circuit, like a wall outlet, and make sure your meter is working properly before you go test in the box to make sure that your the meter reading is accurate. And honestly, what the NFPA 7D standard says is you should test a known circuit. You should, if you're looking to make sure that something is not energized, you should test a known circuit. You should test what it is that you're looking for voltage on, and then you should go back and test a known circuit again to make sure that your meter is working properly. All right, and then the last step is to read the manual. You should have done that before now, but every inverter manufacturer has slightly different startup procedures. Some of them are really, really specific, like test the ground fault fuse and then push this little tiny button that you didn't know existed. And so you really should read the manual and just do what it says. Some of them say turn on the AC first, some of them say turn on the DC first, some of them you need to run through some screens and do some programming. So just read the manual before you throw any switches. You notice step 10, we still haven't turned anything on. At this point, we're saying, okay, everything's wired up correctly, system's good to go. Now we're going to read the manual and figure out how to turn the system on. Well, that's the end of the slides. I said I was going to show you all a few pictures. I can do that. I'm going to figure out the best way to pull up some pictures, and I'll show you all some pictures for just a few minutes. Okay, so I'm going to turn off the webcam and exit out of this, and then pull up some pictures. Let's see. And let me know if you've got questions about this safety presentation. Okay. I think that's it. There'll be some good pictures. Let me make sure. Okay, these are pretty good. So this is that same array that can you see this okay? Just type me a chat message if you can't see this okay. This is the same site that I showed you that aerial view of. This is in Bunn, North Carolina. This is just, looking at the racking from the side. You can see the fence over here. Looks good. Okay, you can see the fence over here. This is a very narrow part of the array, one of those little wings on it. This is a Schletter rack with the driven metal piles. So there's two modules in the portrait on this rack. There's probably some extra pictures in here. This is looking up from underneath the rack, and there's some actually pretty interesting things going on in this picture. One of which is, these are the home run conductors coming from the string wiring right here in the middle, the black and white wires. And you can see that they put this little protective rubber gasket over the edge of the rack. So this is between two sections of rack, and they put these protective gaskets so the wires don't get rubbed on the edge of the rack. And they also put this bonding jumper right here. So you see this strap? That's a braided strap that's bolted to the rail. So that is the equipment grounding conductor that's bonding the sections of rack together. So these are very long rows of rack, and between every two racks there's a bonding jumper that maintains the electrical continuity between the racks. You can see here, this is a picture that's further back. They haven't done all the wiring yet, so you can see that little bonding jumper right there in the middle. This is a guy, and he is wiring up a combiner box that's mounted adjacent to the back of the array. And he's not wearing PPE. He should be wearing safety glasses. He might actually just be cleaning out the box because there was little metal shavings in the bottom of it. But none of this is energized yet. So you can hardly tell, but those are the fuses right there. You can see that the fuses are open. They haven't closed the tip-out fuse holders yet. The box is not quite totally wired up, but the touch-safe connectors on the home runs have not been connected yet. So it's actually, there's nothing in this box that's energized yet. So it actually is safe for him to be working in there without insulated gloves on. So all the wires come in this big LV right here into the top of the box. I wish they went into the side of the box, but I don't always get what I wish for. If you've got a combiner box like this, it's a lot better to come in from the bottom or the side rather than the top. It's just better for water penetration issues. But, you know, oops, every site's a little different. I take a lot of pictures when I'm on site. Some of these are not going to be very interesting. You can see that they put this insulated bushing on the conduit so that it doesn't abrade the wires in the box. Here's a close-up picture of those tip-out fuse holders, and they've got their labels on the string wiring. This is the ground, equipment ground that goes to the rail and grounds the metal of the combiner box. That's just a little equipment grounding conductor. That's a little jumper right there to ground that combiner box. That is a crimp-on terminal lug. They were using aluminum feeders, and they had the right tool here for crimping that lug onto the output circuits for the combiner box. I was just looking at their tools that they were using. That's this Burndy lug crimper that they were using on site. The guy thought it was funny for taking a picture. So he was just getting ready to crimp those terminals on these big aluminum output circuits that run over to the inverter. I'll go through these. There's some more interesting pictures a little later on. So right here you can see the inverter pad. Got some better pictures of it. So that is a big concrete pad, maybe a little overkill. I showed you an overhead picture where the inverter pad was. So there are 4 inverters on the inverter pad, and there's also some data monitoring equipment. So this is the data acquisition system. There's a meter, there's temperature sensors. There's a little transformer right here. That transformer is for site power because there's no site power otherwise, because we've got the PV feeds the inverter and then it feeds straight to the utility grid. There was no 12240 available, so they put in this extra transformer that transforms from the medium voltage to site power. So you can plug in tools, you can have lights, you can have outlets, you can also run the data monitoring system. So it's very typical to see a small transformer on a large site just for site power. These 2 guys are taking their lunch break, and I've got some pictures. This is probably a little bit complicated to talk about right at the moment, but basically what this is a control circuit for contactors in the combiner boxes. So you can have contactor combiner boxes where you've got an electronic control circuit that will open the contactor and shut off the combiner boxes. So it's really useful for roof systems. It's not that common on ground-mounted systems, but we were kind of experimenting with it at the site to see if it was a good idea. It turned out it wasn't that great an idea. I mean, it works fine, but it was maybe not precisely the right thing for that site. For operations and maintenance, it's a little easier to do some other things. So that's the control circuit for the contactor combiners. This is the AC switchgear. So what this is it's a big AC disconnect between the inverter and the transformer. So you can shut off. It's just a big AC PV equipment disconnect. It's also a system disconnect so that you can service the inverter without it having energized terminals in the inverter. And yes, it's gigantic, but that's the way it goes with these systems. So you can see it's 3-phase power. So there's 3 hot lines coming into the switch, and it's also fused. It's a fused disconnect. Let's see. I'm not sure. Let's see if you can see the fuse rating. No, I think that those are. I can't remember. I might have a close-up picture of them. I don't. But at any rate, that's the cabinet right there. So it's a fused AC disconnect that is the output of the inverter prior to the transformer. Oh, there we go. Those are. I still can't read it. 600 volts. I've got a better picture. No, I don't. Can't read it. I don't know what size fuses they are. They're pretty darn big, though. This is inside the inverter. This is the DC inputs to the inverter. So do you remember back in the combiner box I was showing you the crimp-on terminal on those big output circuit conductors? So those output circuit conductors run over to the inverter, and the overcurrent protection device is actually in the inverter. This is about probably a 300 amp fuse that is on the DC side of the inverter. So multiple combiner box outputs run into the inverter cabinet and our fuse. So it's just like a small combiner box, except it's gigantic. And instead of having tip-out fuses, you've got bolt-on fuses. And that contactor combiner that I was mentioning, if you wanted to de-energize these fuses, you can use that contactor in the combiner boxes to de-energize the fuses so you can work in here. So the contactor combiners are the DC disconnects, and that big AC switchgear is the AC disconnect. This is the transformer. So there are 4 AC switchgear boxes from the inverters running into the transformer, and that's why there are so many wires in the transformer. They're all hanging on those big buses in there because there's multiple inverters feeding into the same medium voltage transformer. So you can see the 3 lines, line 1, 2, and 3, and then this is a neutral right here, that gray wire. And you can't see it, but there's also equipment grounding conductors, but they're all in the bottom right there. I don't know if I've got a close-up picture of that. So those are all that's the power coming from the inverters into the medium voltage transformer. There's also some sensor wires on here that feed back to the data acquisition system. All right. The other pictures are just sort of in progress pictures. That is the utility point of delivery. So this is where the output of the transformers feeds up. I know it looks so small, doesn't it? Feeds up into the utility grid. So you can see those 1, 2, 3 lines. But there's 2 transformers on the site. The transformers meet up, and then they feed up into these power lines. And these are called fused cutouts. Those are insulators, and then there's a fuse, and there's a little ring on it, so you can use a hook to open up these fuses, and that's the point of delivery to the grid. Let's see. I think I just took some more close-up pictures of the 15 amp fuse. I don't know if there's any other really interesting pictures in here. Maybe one other thing I'll show you is I'll show you some of the pictures of the aerial photos of the O2 sites just because I think they're cool looking. This is Ararat, which is up in Mount Airy. This is that same site we were just looking at from a different perspective. This is Bunn out in Bunn, North Carolina. You can see the prison very well in this picture. This is Sandy Cross, which is near Rocky Mount, North Carolina. This is about, those other 2 systems were 3.5 megawatts. This is 1.5 megawatts. I really like this system. It's lovely, but it also, the power, it's next to a vineyard and it's owned by a winery that grows grapes. And they grow grapes here. This is where their vineyard is, and then the winery is in Erie, North Carolina. So it's for a North Carolina grape growing family. There's actually a little family cemetery plot right here, which is why the array stops here, is because we didn't want to interfere with the cemetery on site. All the guys went fishing when they were building this system. This is a system that's in Robeson County. It's another 3.5 megawatt AC site. There's actually, it's not quite finished in this picture. You can see the modules still missing up here on the top. There's 3 inverter pads at this site. There's one there, there's one there, and there's one there. There's 7 inverters on this site, and then it feeds out to the grid right here on the highway, actually right across the highway. And then one more. This is also in Robeson County. It's another 3.5 megawatt site. There's just 2 inverter pads on the site. There's one right there, and there's one right there. And then it feeds out just in a straight line out to a point of delivery on the road right there. So maybe what I usually do, I don't know if I can find it right now, but what I'll do, we're going to have our review session next week, and I'll show you some more pictures of different residential interconnections. That was sort of very large-scale system interconnections. I'll show you some pictures of smaller residential system interconnections because there's multiple ways to set up the equipment in terms of, 2 meters, 1 meter, line side, load side, supply side connection. So I'll show you some pictures of those when we do the review section because I am running out of time. And but I do want to show you some more system pictures. Or if there's any other, if you want to see specific pictures of anything in particular, I have literally thousands of pictures of PV systems. So if you're like, I want to see a picture of X, I can pull it up. You know, this is, I have 2,467 pictures here of PV systems. So I kind of collect PV system pictures. So if you want it, I probably have it. So Jason S. has a time been set for the 11th, and I don't know. Maria will send out an email. I don't know what the time is yet, but she'll send out an email to all of us. And if you can't make the time, then it'll be recorded. And just try and send me your questions beforehand, or if there's something you specifically want me to show y'all, just let me know beforehand. Okay, like I said, they'll send out a notice. Yeah. All right. And so just a couple other wrap-up things. I hope you all enjoyed the class. Like, we're going to have this one more session next week, so it's not quite the end of class. I hope you all enjoyed the class on Friday as well. I think that should be a lot of fun. If you've got entry-level exam type questions, you know, please let me know, because we can do some of that review next week too. And if you're looking for a job in the solar industry, holy cow, there's a lot of jobs right now. The North Carolina Clean Energy Technology Center newsletter, they had links to probably 5 or 6 jobs. Solar Pro, yeah, check the newsletter. There's a lot of jobs. Solar Pro magazine has a job section, and I was looking at it just this morning because it came in an email, and like half of the jobs were in North Carolina. FLS is hiring, Sundance Power is hiring in Asheville, Strata is hiring installers in Chapel Hill. You know, there are tons of jobs. You can look on LinkedIn. It's like, I don't know if any of you are looking for a job, but if you are, there's no shortage of PV jobs in North Carolina right now. So, you know, check the newsletter, check Solar Pro magazine, send me an email if you're looking for a job, but probably you'll do better off just, you know, search it on the internet, because there's so many. The NCSEA website, yeah, tons of jobs. So on that note, I guess I'll call it a day. Yeah, and I hope some of y'all join me next week too, and keep in touch. Let me know where you go and what you're doing, and I'm always at all the solar conferences. I go to them all. I'll be at the NABCEP conference in March in Albany, New York. I'll be at InterSolar next July, and I'll be at SBI next October. So I'm pretty easy to find if you if you're going to any solar conferences. Track me down. All right, y'all. Well, enjoy the rest of your day, and